Okay. So let me now show you the code that implements what the method value shows. So see correctly. Okay, so I'll try to be a little quick. So this is once again solving the Helmholtz equation in 2D here. Okay, and so these are some physical parameters. So this will be our tolerance for the iterative schemes. We will be doing P2 finite elements. This is the frequency for the Helmholtz equation. This is the number of points per wavelength. And I will be using FFDM just to in order to build the non-overlapping partitioning. And so this will be my velocity, acoustic velocity, C. So for now, I will just use the reference velocity of C and show you the homogeneous case. This will be my wave number K. This is the reference wave number because we use as the coefficient K in the definition of the hypercellular operator for the impedance operator. Since I need a constant. Okay, the wavelengths. And so we'll be doing impedance boundary conditions on the 4 boundaries of my rectangle domain. So I have my rectangle domain here, mesh TH and 2D. This is just doing some mesh adaptation that I will show the result of the mesh adaptation in the heterogeneous scale from a velocity with a velocity model coming from the well-known Marmoussy acoustic model in 2D. And so basically the idea is to adapt the mesh to the local wavelengths. Since I have a heterogeneous wavelengths, I have to have a near optimal mesh in terms of mesh size. Okay, and this is my point source, which is approximated in resolution located at the top of the domain. And this I will just use FFDM to build the non-overlapping decomposition of my volume domain. So overlap is 0. So the overlap is only the interface of the skeleton between the subdomains. And so then I can just plot one is a subdomain of 0. Right? Okay, so I'm doing 8 cores. So we assign 1 core per subdomain. So this is a parallel script. And so I will have 10 subdomains. And so this is my decomposition, okay, of my mesh. So we see the skeleton, the interface with subdomains with some cross points here. So we see the lattice decomposition. And I see that I have 13% batteries. Since I will be running the scripts, it might. And so for example, this is subdomain 0, right? The decomposition. Okay, and I will also be the distributed finite element space on this decomposition. Once again, this is FFDM. So this is all volume stuff for now. And then I will be able now to define my AIs as in Xavier's slide. So the local matrix in each volume subdomain omega I. So I have my variational formulation here, which is basically the local Helmholtz equation in a local mesh THI with the Robin boundary conditions in the four boundaries. This is my right hand side for the volume source, the point source. And now I can build my AI matrices. So it's in the parallel script, right? So each MPI process will build only its own AI matrix corresponding to the local subdomain. And then I will turn on what's going on the skeleton. Okay. So as I said, using the extract keyword, I can extract the interface to the subdomains. And so the interface level on each subdomain on the subdomain interfaces is FFDM interface level, which defaults to 10. And so I just want to extract the interface between subdomains in my gamma I mesh. So I can also plot gamma I. here. That's a simple. Okay, so yeah, this is the volume left, and this is the gamma I corresponding to the interface of this subdomain 0. Okay. Okay, and so now I can define my finite element space and this gamma I, so my local finite element space in gamma I, and then I have the interpolation, so the restriction matrix between from the volume finite element space to the boundary finite element space. So I interpolate VHI to gamma VHI, and this gives me a restriction matrix. And I also put it in the complex format because I will be doing matrix vector products and matrix products with complex matrices, so everything needs to be complex. Okay, and so now I am able to build my TIs, right? So these local impedance operators in each subdomain. And so in each subdomain, so for example here, you see the commented version is a simple impedance, delta impedance operator, so it's just a local mass matrix on gamma I with 1D integrals, if we are in 2D, boundary 1D, and just a mass matrix with the K. So this will give me a sparse matrix. But as Xavier said here, we can make use of the boundary of method in FreeFem to build the hypersimilar operator. And so once again, we have a variational formation, which is a double integral in gamma I. And my kernel is a hypersingular operator with a full imaginary K, right? So I, K is 0. And so I can build the H matrix corresponding to this variational formulation. For example, here we choose the compression method in HB. And the important part is that we need to specify the enclave communicator for this matrix, because by default, H2 will be the parallel matrix with all the processors in the default communicator from one. But here we are defining a local H matrix in each subdomain. So my communicator is only me. So I need to specify that the command is a empirical set, because every H matrix is local to subdomain. So I can display it. And then for simplicity here, since I will be using, we are still trying to compare methods. Every TI will be in the sparse matrix format, right? Because I don't want to change format everywhere when I try another impedance formulation and so on. So I need to densify the matrix. First, I densify this H matrix and put it in a dense matrix, and then I sparsify the dense matrix in order to have the same format for every try we do an impedance operator. If I put this in TI, you can also print some info on the H matrix. And so now I build my TI. And so now I can build the matrix we need to invert the algorithm, so which is AI minus, I think it was notation G or G transpose TIG, so basically plunging TI in the volume numbering, right? So I need to do RI transpose TI RI, and then I do AI minus I this matrix, and this will be my local matrix, volume matrix that I need to invert in the subdomain. So here I use nums as the solver. Once again, since nums is a parallel solver, I need to specify that I'm doing only local matrices here in each subdomain. Okay. And so this is a little trick. So now this TI is these TIs are the building block for the full impedance operator T that I need to invert, and I will basically do that to PET-C and can do any solver in PET-C to invert T. Okay, and so the little trick is that PET-C needs the partition affinity, but there is no partition affinity in the algorithm because the T is the sum of the TIs, and so since the partition affinity needs to sum to 1, I basically give a partition affinity to PET-C, which is just the restriction of the partition affinity in my volume decomposition. So this will since I have non-overlapping decomposition, this is just 1/2 almost everywhere on the skeleton, and 1/n of the close points, usually 1/3 or 1/4. I need to sum to 1. And I just divide my TI. So I multiply by the left multiply by the inverse of this diagonal partition affinity, and do that to text. This is just some stuff to be able to define the right restrictions between boundary subdomains, because we have some overlapping, some shared degrees of freedom, obviously, in the skeleton. So I need to be able to do that communication pattern to Patsy. Okay, and so now I'm able to define my T operator as a distributed set mat, right? And so I put basically I use the TI on each rank with the intersection on the skeletons between subdomains, the partition affinity, and the communicator. So this time this is the distributed operator that I need to enter. And so for example here we can use multi-grid, we can use direct solvers, but Jacobi and so on. So maybe let's just first use LU, and then I will be able to just use just define as in the algorithm Xavier showed the operator that I will need to use in order to solve the outer problem with GMI. So this is just a matrix vector product, a custom defined function that takes a little distributed vector on the skeleton as input. And basically the code just reads like the paper. So first we need to multiply by TI. Then we need to put the result in the global numbering. So extension using the restriction matrix, transpose the restriction matrix. Then we need to solve with the local volume matrix Li. And then we need to apply T. So basically sum of TIs. So I restrict again. Oh no, so not yet. Sorry. So this is just restriction. I restrict again to go to the subdomain number multiplied by TI. So this is just as it's written in the algorithm. And then I apply T. So sum of TI basically, so everyone multiplied by TI, and then I synchronize on the overlap regions of the skeleton by using the exchange operator of the Patsy matrix. And then I can solve, then I need to apply T minus 1. So I just write T minus 1, and this will be Patsy that will solve the problem. And then that's it. I'll just combine the results with TI. And this is my operator that I now use in the GMRise algorithm. Okay, so this is just the right hand side for the volume problem. So now I need to transform the right hand side to get the correct right hand side on the skeleton. So this is just another algorithm that goes from the right hand side, volume right hand side to the right hand side on the skeleton. And then once again use Patsy in order to basically use the shell matrix of Patsy in order to wrap my operator and give that to Patsy. I will be able to solve it by GMI. And so I need to basically, as Xavier said, it's a block diagonal operator, right? So for this matrix, there is no intersection because it is the product space of the gamma i's. And so I have a partial affinity that is 1 and no intersection. And I give that to Patsy to do the shell matrix and wrap my operator. And then I can once again solve the problem with GMRS, for example, or any iterative method using Patsy like this, with any Patsy flag. And then I have my solution on the skeleton, and I can pretty easily go back to the volume unknowns to get my final solution. And I can take. So try to be quick, so let's do that. So here I have an vector with frequency 10, for example. This is in a homogeneous case. So this is the H matrix on rank 0. So you see the basically using the LVD for compressing the blocks. Okay, and this is the final solution. So this is just an analytical solution. So you have some pollution effects here because you only use one first order impedance boundary condition as approximation of the transparent boundary conditions of the interfaces. So especially on this boundary, you have some spurious reflections because the approximation is poor. But here we see, okay, since I switch to LU, right, for solving for T, I have only one iteration for each resolution in T in the inner loop, right? And there, then I can convert the outer problem in 40 iterations. Okay, and you can see if I increase the frequency, it will take a little bit more time. Not too much. Okay. So we have now 200,000, almost 200,000 degrees of freedom. So you see, for example, here, this is the time it takes to assemble the TI using the hypersingular operator, so less than 1 second. And this is the stats of the H matrix. And once again, so now we convert in 46 iterations. So it's pretty robust in terms of increasing the frequency. And so within the same script, now I can show you what's going on if I use a more interesting velocity model. So let's use Marmisi here as my velocity model. Okay, and then I will also, this will now be useful. I will adapt the mesh to the local result which is now heterogeneous. So let's go back to the you see the mesh starting to be, we see a little bit better in the higher frequency, but this is the adapted mesh. And this is the solution at 10 Hz. So once again, 43 iterations, so it's pretty robust with respect to the heterogeneity. And I can also increase the frequency. So now everything is basically unstructured. We have unstructured heterogeneous mesh, unstructured partitioning, cross points, but we don't really care about that. Everything is robust, so that's pretty. That's the good news. You see the solution at 20 Hz, so 48 iterations. You can go on including the frequencies, and basically I will just conclude by showing some larger scale results. Since also in Marmisi, because it is preliminary results, so we are still in 2D. We are doing 3D right now, but the results are not really ready to. We are still experimenting that in 3D because it's a little bit more costly to do the hypersingular operator and so on. But this is exactly, so the script I showed you can also be run on a supercomputer. This is exactly the same script that I showed you. So this is the velocity model of pharmacy that I just showed you, right? And see if we do P2 with 8 points per resonance, and we increase the frequency here, we go from 3 million degrees of freedom to 200 million degrees of freedom. And n will be the number of subdomains. Okay, and so for a given frequency, we see that when I increase the number of subdomains, I basically increase the number of iterations like square root of n, which makes sense because this is still a one-level method. So basically, the number of iterations grows like the number of subdomains in one direction. Right? So square root of n in 2D. But if you increase, if you go up the frequency and keep the same number of subdomains, you can see that the number of iterations are pretty steady. So it's the good news for the future, I guess, because these are still preliminary results. And I just end up with the full picture at a very high, at the highest frequency, 40 Hz of Marmisi. So this is the real part of the acoustic field, and you can see we are able to solve particular problems with a lot of wavelengths. So this is still 2D, of course, but and so I will stop here. And maybe answer any question if you have.
Okay.
So this was a little bit of a sneak peek with Platzi of what you can do with Platzi in FreeFem, but we'll go into more details and see all the capabilities of the up-to-date Platzi interface with Pierre this afternoon.
Okay. Some question,
Lorenzo, we have a question.
except Pierre. And maybe there are questions under the chat.
Yes. Hello.
Hello, where are you?
Thank you for the presentation. I would like to know in this Marmoussi example where there is several wave speed and stuff like that. How do you choose the kernel? Is it changing with respect to the velocity in each subdomains, or is it just an ad hoc choice? And can you comment on that, please?
So maybe I can answer first, Pierre-Henri. So first of all, I need to underline that the choice of the impedance does not need a priori to be related to the wave propagation problem. I mean, the convergence is guaranteed no matter the choice of the impedance, provided that it is coercive. That it is a coercive matrix. So that's first point. Of course, if you choose this impedance in a smart manner, which means that it needs to be related to the problem you are actually solving, then the convergence will be faster. Here for the numerical example that the numerical application that Pierre-Henri has shown, we choose a constant wave number that does not vary across the computational domain. Yes, and this is an average wave number, I guess, but maybe now, Pierre-Henri, you can confirm.
This is with the reference. Basically, I use this reference velocity C0, which is a little higher than slowest velocity, right? And so basically, I could also take slowest velocity. I think the idea is that it works well if you can resolve for the highest velocity, right? For the lowest velocity, which means highest, lowest present. No, so smallest present. Sorry. No, largest present. Sorry. But in practice, I think I gave it a few tries, and it seemed to work better if I choose something around the smallest velocity, and it degrades a little bit if I choose a constant velocity closer to the largest velocity of the model. But it doesn't make that much of a difference. But you're right that we need to make a choice because it has to be a constant, and it is not a constant in the domain. So it is kind of heuristic for now, but it seems to be pretty robust with respect to the choice. Obviously, if I put 100 instead of 2, it would be very bad result. So you need to be somewhat in the range of the velocity of the model.
But nothing prevents from taking a wave number, a different wave number in each subdomain. You may consider an average wave number, wave number, average wave number local to each subdomain.
Yeah. So I also tried that, and it doesn't seem to change much. Not take it constant everywhere for now. But this is acoustic models. The velocity range is not that large, right? So from 1.5 to 5.5 is very low contrast compared to, for example, elastic wave simulation. And so probably it will have more impact when we move to higher contrast, for example, for elastic waves to wave propagation.
So in your script, so I have two questions in particular. At one point, you have like FFDM macros where there are just commas and no parameters. In the mesh, so it's just to specify.
Yes. So,
no basic, right?
yeah, so I didn't go into the details, but here usually you have a user-defined prefix in order to have multiple decomposition or multiple finite element space, distributed finite element spaces in the same script. But here, since we only do one thing, you can also have an empty prefix. That way, the local mesh, for example, is called THI, which normally is, for example, VHI here might be prefixed with my prefix THI. But since it's empty,
Sure.
but yeah, it was for simplification, but it
Yeah.
actually maybe leads to more confusion.
Okay. And so at one point you define the partition attribute for the TI, I think. Yes, here with the inverse of the multiplicity.
Yeah.
And so would that make sense to only put either zeros and ones? And so, for example, one on master interfaces and zeros on slaves interfaces, let's say, or do we need to have the multiplicity scaling?
Yeah, I think I think it will solve my problem of needing to do that. So I think if I take only 0 on 1 starting affinity, I probably don't need to do that.
Okay.
Yeah, so I could have done that.
Right.
Yeah. I think if there are no more questions, I guess it's time to go. Maybe I let Frederic conclude mine.
Yes, so thanks again. The first conclusion. Second conclusion, merci d'être venu. Merci de participer à Zoom. On va essayer de manger. Et puis, on va reprendre à peu près 1h30 si ma mémoire est bonne. So we restart at 1:30. With, I think, a new Zoom session number. So be clever. I send all the information by mail, or you can have that on the web page for this afternoon. And after, for the tutorial part, we have 2 links of Zoom, and all the information will be on the web. So, see you tout à l'heure, comme on dit en bon français.